Selection rules for scattering are basically similar for different types of problems if you consider them from the right perspective. I mean, optics, acoustics, water, it doesn't really matter, they are similar. But as a scientist in optics, I will talk mostly about optics, probably a bit about acoustics, but anyway, it's all about symmetry again. By the way, my name is Christina and I have many other videos about various optical topics. If you happen to find this video somehow, YouTube seems to think my videos are so bad that they shouldn't exist at all. So if you share this with at least one person who might be interested, I would really appreciate this. Our scattering problem is formulated as follows. We have some incident wave of a particular shape, say a plane wave or vortex beam, and some scatter of a particular shape, for example, nanoparticle or resonator or something. So the problem basically has some axial symmetry. The incident wave has its symmetry and the resonator has its symmetry. We will need two letters here, M and N. N will denote the symmetry of the resonator in a simple, intuitive way shown here. I mean, if we rotate the resonator by 2p divided by n, it coincides with itself. That's all we want to know. The exact shape doesn't matter. Okay, here the resonators also have reflection symmetry, which matters as well, but we'll discuss that later. M is responsible for the symmetry of the incident wave and the scattered wave. So basically we have two M's, one for incident wave and one for the scattered wave. What we are looking for are the possible values of M for scattering. But what is M? We will call M the total angular momentum projection, but it is probably not the best name. M describes the behavior of the wave under rotation, basically of a function under rotation. For example, if you take a circular polarized plane wave and rotate it as a whole around the z-axis by some angle alpha, the only change is the additional phase, which equals e to the power I alpha. If you take a vortex beam with the total angular momentum projection m, under rotation it will acquire the phase e to the power I m alpha. Basically, this m is by definition the characteristic of this rotational behavior. In the multiple language, if we decompose everything using vector spherical harmonics or multiples, you can find my video on multiples in the description. This simply means that if the wave consists of multiples with a particular m, then the wave has this m. This is because the number m of multiples is exactly the total angular momentum projection. And multiple order decompositions of beams are known from literature. Usually when talking about beams, people talk about so-called spin and orbital angular momentum. I will probably end up living in the street in 2 years because of this, but the spin of photon is not well defined. If we assume the definition of spin as written in this book and as shown here, an orbital angular momentum as well. One can even consider irreducible representations of the Poincare group and get the same result. In the paraxial approximation, we can probably introduce these terms formally, but this is only an approximation, and in contrast, working with total angular momentum doesn't require any approximation at all. A photon has also helicity instead of spin, and vortex beams usually have well-defined total angular momentum projection and helicity, but in most real-life problems, helicity is not conserved anyway, so we will simply ignore it here, because no specific selection rules appear unless you choose a very specific material. Please check this fantastic book and the links in the description. I'm not a particle theorist, so I can't tell you much more than that. Well, okay, we have an incident wave that has some m, and we have a nanostructure that has some n, but we don't want n, we want something like m, because we want to use total angular momentum conservation, not exactly conservation, addition. So let's take a nanostructure shape and try to describe it with the help of some trigonometric functions, because for the functions, for the exponential functions, we can easily define m. Basically, we decompose the shape into a Fourier series, and in the end, we obtain all possible m's that are multiples of n. Then the scattered wave is basically written as a product of the particle response and the incident wave because of linearity and so on. Of course, one can write this in much more detail. See the links in the description. But this term, which represents the particle, should behave symmetrically exactly like the particle itself, of course. And it is described by this Fourier decomposition. So it contains all possible m times z, where z is integer. The incident wave has also some well-defined m. So the possible m's for the output are now obvious, and they are shown here. Okay, the incident wave can also be a linear combination. I'm sure that this is not a problem for you now. By the way, if you use material from this video, don't forget to cite it. So that's basically all, but there are some additional issues. First of all, if the structure has reflectional symmetry, then parity is conserved. Parity under this particular reflection symmetry. If you have an incident wave that is even or odd under this reflection, the scattered wave will also be even or odd if the nanoparticle has this reflection plane. Such waves are usually linear combinations of waves with m and minus m. Indeed, for example, a circular polarized wave does not have a definite parity, while a linearly polarized wave does. In acoustic, everything is basically the same. The only difference is that you need to use scalar functions instead of vector ones, not for every material, but in most cases. Note that for an acoustic wave, the most common plane wave has m equals 0, while in optics it is m equals 1, because we have vector functions. Also note that only m equal 1 multiples radiate in forward and backward directions in optics, and m equals 0 in acoustics. If we talk about different values of m, 2, 3, 10, whatever, the intensity will be 0 in the forward and backward directions. Also, here we have taken into account basically only axial symmetry around the z-axis. There can be situations where the symmetry is higher. For example, a spherical nanostructure irradiated by a single multiple. If you encounter this case, you have to read the paper in the description. But basically, the rules will be either more strict or just the same. Interestingly, we could try to imagine a nanostructure that is not described by an infinite series, but by a finite one. This is not really common in real materials, but in the next video I will explain where such situation naturally appears.